of 2010, there was a hidden aurora found near New Zealand. This was observed from the International Space Station. You're looking at this from above it. And that's obviously, if you'd make a guess, that looks electrical to me, right? And surprise it is. So what we're going to discover is there's a group of pioneers, scientific pioneers, that are all from Sweden or Norway, the high latitudes. Why? Because they're confronted with the auroras. And they got curious, what is an aurora? They started studying. Christian Birkeland is one of those, 1867 to 1917. He made a heroic commitment gathering data. Instead of theorizing, he went out in the cold, long nights. Their nights they go for months, right? And gathering data, risking his life. In gathering that data, he learned a lot about auroras. He was the first to recognize the electric currents flow from the sun to excite plasmas in the Earth's upper atmosphere. He discovered the twisted, corkscrew-shaped, high-intensity currents in the plasmas that follow magnetic fields rather than across them, the so-called Birkeland currents. And he was nominated for the Nobel Prize in Physics 7 times. His portrait remains on the kroner, the 200 kroner Norwegian currency to this day. Interesting guy. He was succeeded by Irving Langmuir, 1881 to 1957, roughly the same birth and death of my dad. It happens coincidentally, that's why I happen to remember it. He discovered the double sheath or the double layer effect in plasma. I'll show you that in a minute. He coined the term, he's the one that coined the term plasma to describe the almost lifelike, self-organizing behavior of these ionized clouds in the presence of electric currents, magnetic fields, and foreign bodies that are inserted in them. These plasmas start to behave in an organized way because of the laws that they follow, which are very different than non-plasma materials. He invented the Langmuir probe, which is used to this day for research here. Now, there's double layer phenomenon. One of the most important properties of a plasma is its tendency to isolate one section from another electrically by a wall of two closely spaced layers. They call that a double layer. One of positive charges, the other negative. It does this intrinsically to protect itself from intrusions. A DL, or a double layer, is where the strongest electric field will be in any plasma will be found. And plasmas isolate themselves from foreign intruders by surrounding themselves with a double layer as a protective sheath. That's just, they have a behavior that's almost as if they had their own intelligence, so to speak. Well, he was followed by Hannes Alfvén, who was 1908 to 1995. Notice we're getting to recent years here. This is a new technology. And this guy was first to predict the large-scale filamentary structure of the universe back in 1963. That's when it first proposed, by the way. He first proposed the mechanism for the acceleration of cosmic rays, now known as the Fermi mechanism. He was awarded the Nobel Prize in Physics in 1970, and on it goes. In February of 1981, 11 years after Swedish electrical engineer Hannes Alfvén won the Nobel Prize in Physics, he published Cosmic Plasma, a book which has been largely ignored by the astrophysics community. And what you're going to see here is stuff that the astronomers, the astrophysicists, have chosen to ignore, to their peril, as it turns out. Our space probes have confirmed his views. So this is giving the point, we've got evidence now combining. Over 99% of the universe is composed of electric plasmas. And they obey, here's the important thing, they obey the same laws as small laboratory plasmas do here on the Earth. We can recreate these shapes and forms in the laboratory. We understand that behavior, and it turns out we're observing that behavior in the galaxies. So you're getting empirical confirmation here. And we get to Anthony Peratt. He's an author of The Physics of the Plasma Universe, which I encourage you to get a copy if you're technically oriented. Numerical and experimental contributions to high-energy density plasma, tense particle beams, explosively driven pulse power generators. You can already tell this thing's getting classified, isn't it? Lasers, intense power, microwave devices, particles, high-energy density phenomena, Z-pinches, and a bunch of other things that I'll show you up here in a minute. He's at the Los Alamos National Laboratory from 81 to the present, serving Applied Theoretical Physics Division, and so forth. And he's also scientific advisor to the United States Department of Energy, where he served as acting director of National Security and Nuclear Proliferation Directorate, and so on. He made large-scale simulations of the Maxwell-Lorentz equations And he was able to yield the same results in those simulations that are indistinguishable from the astro images from actual galaxies. And here's a group of the pictures. These were done in the laboratory, and we see the same shapes and behavior that we observe through telescopes. So it's interesting confirmation. The effects of gravity are minuscule. The effects of electromagnetism can be 10 to the 39 times more. The entire volume of our galaxy consists of magnetized plasma. 99% of all matter is plasma. Here is a picture of M31. You've seen this in all your astronomy textbooks, a very common picture of Andromeda, as it's called, right? That's invisible light. Let's take a look at this in infrared. And you begin to see the electric structures that underlie that thing. And we look at M82, and if you look at it in other frequencies, you realize it's a plasma structure. If you look at it infrared, as you look at these, you begin to realize that there are aspects to those structures that are not normally visible in light. And you can almost see the axis, and you can see the other behavior. Maxwell equations. There are 4 partial differential equations that relate electric and magnetic fields to their sources, charge density, and current density. And these equations can be combined to show that light is an electromagnetic wave. The interactions of electrostatic and electromagnetic forces are very non-intuitive. One of the problems in this area is we're not talking about 1 or 2 dimensional relationships. We can deal with 1 or 2 dimensional relationships. We can't normally deal with mutually orthogonal relationships. I'll show you what I mean. The forces are orthogonal to the fields. And the resulting plasma takes on a unique aspect as a composite body with a very distinctive character. You see, the magnetic field is in one direction, the velocity is in a different direction, and the force these are all mutually orthogonal. Each one is 90 degrees from the other. And that their behavior among themselves is very non-intuitive. You've got to experiment these to get a feeling for how plasmas behave, because these are all mutually orthogonal. Are you with me so far? Okay. In fact, the engineers will speak of a right-hand rule. If you have an electric current, around that electric current, there'll be a magnetic field. If the current is changing, the field will be changing. If the field is changing, the current will be changing. They're intrinsically hooked, and they're hooked with what they call the right-hand rule. You put your thumb in the direction of the current, your fingers will point in the direction of the field. You with me? They're inextricably linked, okay? You don't have one without the other. And that's the net of those equations, the so-called right-hand rule. Now, it turns out that plasma you don't normally see. It has 3 modes. It can be dark, where there's no light admitted. You don't see it normally. The Earth's ionosphere, except during auroras, is invisible, okay? Electric current, if the current is very, very low, you don't see the plasma. Now, you add a little more current, it goes in what they call the normal glow mode. When you see a neon sign, that is in the glow mode. It's a plasma that's going through that tube. It emits light. Auroras, emission nebula, the sun's corona, and comet trails are all examples of plasma that is in normal glow mode. The brightness and intensity of the current and density of the plasma and so forth. The color depends on what gas is being ionized here. Okay. Then you get to the bright one, the arc mode. You got dark, normal, and then arc, which is extremely bright and a very wide spectrum of emission. Electric welding. You never look with unprotected eyes at someone doing electric welding, because you're seeing an arc, and it has frequencies that'll hurt your eyes. The sun's photosphere. You never look directly at the sun. And lightning. Fortunately, it's so brief it won't do that much damage to you. And sparks are examples. It's characterized by twisting filaments, both in the ultraviolet and in the radio frequencies. We also encounter a strange thing called the Z-pinch effect. High-intensity current passing through a plasma will take on a corkscrew or spiral shape. This was discovered by Birkeland, so they're called Birkeland currents. They most often occur in pairs, and they tend to compress between them any material, ionized or not, in the plasma. And they call this the Z-pinch effect. I'll show you that in the diagram here in a minute. Cosmic matter tends to form an abundance of these filamentary, stringy kind of structures. The initial velocity of a particle is perpendicular to the magnetic field. The path that the particle takes is a circle in the plane perpendicular to the field. However, if the initial velocity of the particle is at an angle different from 90 degrees to the magnetic field, perhaps slightly in the same direction as the field, then the path will be a helix or a spiral. The stronger the field is, the smaller the radius of the circle will be. No matter what the initial direction of the current stream, it will end up following the direction of the magnetic field. And here's a diagram of that. It's called a Birkeland current, okay?